Greetings and welcome to Probability Topics, Lesson 3.5, Tree and Venn Diagrams. Don't skip this important step. Go through each of your new terminology for this lesson. One time or another, you have probably seen a type of tree diagram. One of the most commonly used ones is called a family tree, where you can take some long lost relative and trace back who their children are, and if they had children, and if they had children, and if they had children, all the way to your grandparents, then your parents, then to you. And then if you had any children, there would be a branch off of yours. You've also probably seen something called a decision tree, especially for games. And maybe you haven't seen the actual tree, but you've certainly made these decisions. So I don't get much downtime, but I do like to play the Zelda games. And if I have more than 5 hearts, then I'm ready to enter the castle. And if I have my particular weapon, I'm ready to fight the boss. If I don't have the weapon, then I have to find the treasure chest with the weapon so I can then go back and fight the boss. So this decision tree depends on my circumstance. In this case, the blues are the circumstances and the yellows are the outcomes that I would do. So if I don't have more than 5 hearts, I'd try and go find a fairy fountain to fill my hearts. If I do have more than 5 hearts and I enter the castle, but I don't have the particular weapon, well, then I'm going to explore the town if I don't enter the castle. If I don't have the weapon, I'm going to find the treasure chest. So this type of decision tree could lay out your strategy for a game. What we're going to deal with is regular tree diagrams to where we can look at probability of events. So each intermediary step will lead to an outcome. So for example, I can either flip a head or a tail. They have a 0.5 probability of occurring. And then I flip another coin, and from each primary coin, the first one, it branches off into 2 new branches. I could have rolled a head, a head tail, a tail head, and a tail tail. Now you've seen this before. We've plotted it out different ways, but now you're going to start using these tree diagrams to figure out what your outcomes are and fairly quickly figure out the probabilities. Let's look at a tree and decipher what's going on here. We need a little bit of background information. So in a bag, there are 11 balls. 3 of the balls are red, we'll call those R, and 8 of the balls are blue, we'll call that B. The tree diagram uses frequency to show all the possible outcomes. Now it doesn't list all of the outcomes, but it does let us know how many there are, the frequency of them. Let's talk about the tree. When we first draw a ball out of the bag, there are 8 blue to choose from and 3 red to choose from. Those are the 2 branches, 8 blue, 3 red. And whatever ball we pick, we put it back in the bag. And we pick again. Now, if the first we pulled out a blue and put it back, there's an opportunity to pull in one of the 8 blues or one of the 3 reds on the second draw. If we initially pulled out a red and put it back, on the second draw, we still have the chance of 8 of the blue or 3 of the red, because remember, we put the ball back. What this also shows us is how many outcomes there are of each kind. Blue, 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 red, red, blue, and red, red. If we drew 2 blue, one on the first, one on the second, how many chances that we would get that? There are 64. 8 blue the first time, 8 blue the second, 8 times 8 is 64. Now let's go down another arm of the tree where we picked a blue first, then a red. Well, there's 8 chances of picking the blue the first round and 3 chances to pick the red on the second round. 8 times 3, 24. Now, if we pulled red the first draw and then blue the second draw, that's 3 times 8. There are 24 chances of getting a red ball first, then a blue. Lastly, we could have pulled a red first and a red second. Well, there are 3 opportunities to pull a red the first time and 3 the second, so 3 times 3 is 9. Now, here's why there's so many opportunities. There's actually a total of 121 different ways to pull 2 balls out of the bag. 64 blue-blue, 24 blue-red, 24 red-blue, and 9 red-red. Let's number the balls that are in the bag. So, like the lotto in California where they have those balls in a big rotating drum and they pull out the ball and they say, oh, it's 32. Well, we're going to number these balls and put them in the bag. And because they're just colored, we're just going to say B1, B2, B3, B4, B5, B6, B7, B8, because there are 8 blue ones. And then for our red ones, we'll have R1, R2, R3. Now that we have each of the balls in the bag labeled, how can we draw the ball out of the bag? Well, let's just say that we draw a blue one first and it's labeled B1. We put it back in the bag and we could select B1 again. So that's B1, B1. And first we pull out B2 and put it back in the bag, and next we pull out B1. So you can see all these different combinations that we can do. There are 64 of them. So for every B1 pulled out the first, we can go B1, 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 B2, B1, B3, B1, B4, B1, B5, B1, B6, B1, B7, B1, B8. So for every ball, there are 8 possible ways. 8 times 8 is 64. Now, if we look at the possible ways to draw a blue first, then a red, remember there are 8 blue, and 3 red. So it could be B1, R1, B2, R1, B3, R1, B4, R1, B5, R1, B6, R1, B7, R1, B8, R1. And then we repeat it all with R2, and then repeat it again with R3. How many ways to pull the red ball first, then the blue? There are 24 ways. So just to name a few: R1, B1, R2, B1, R3, B1. Repeat again with B2. Repeat again with B3. Repeat again with B4. You can see them all listed. There are 9 ways to pull red, red. R1, 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 R2, R1, R3. R2, R1, R2, 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 R3, because we're replacing the ball. And finally, R3, R1, R3, R2, R3, R3. Now, I said calculating probabilities was going to be fairly straightforward with using a tree, and it is. Let's look at that first draw. What's the probability of getting blue? Well, there are 8 out of how many balls? There are 11, so 8 out of 11. So 0.7273. How many reds are there? There are 3 out of 11, and therefore 3 divided by 11 is 0.2727. Now you can see if you travel down the lane, down the branch of the tree, if you do blue, blue, it's 64. Well, we got that 64 because we said 8 times 8. Well, the probability of getting the blue is 8/11. The probability of getting another blue is 8/11. So the probability of getting blue, blue is the probability of blue times the probability of getting blue. 8/11 times 8/11, or 0.5289. These are mutually exclusive. Remember, we're putting the ball back, so you can't draw a purple ball, which would be red and blue. They're completely mutually exclusive, and therefore, blue given you already drawn a blue is just probability of blue times probability of blue. You can see where we're going with this. The probability of BR, well, that's going to be the probability of B times the probability of R. Well, 8/11 times 3/11 is 0.983. Now, it doesn't matter in which order we multiply, so the probability of RB is the same thing as BR. Probability of red times probability of blue is 3/11 times 8/11, which is 0.1938. Probability of RR is the probability of R times probability of R. 3/11 times 3/11 is 0.0744. When we're calculating an OR probability for mutually exclusive events, it's pretty straightforward. For example, let's say we want to draw one red ball and one blue ball, but we don't care in which order we get it. So it could be an RB or a BR. When we have an OR, we're just going to add the two together. So it's going to be the probability of RB plus the probability of BR. Probability of RB is going to be 3/11 times 8/11 plus 8/11 times 3/11, and therefore we get 0.3967 after figuring out all the math. When calculating AND probabilities, it sounds like it's more difficult, but it's actually something we've already done. What is the probability of drawing a red ball on the first draw and a blue ball on the second draw? Well, that's the probability of R first and B second. When we look at our trail, that gives us 24 RB possibilities out of the 121. In other words, 0.1983. But another way of looking at it is probability of RB. R came first, B came second. So that would be the probability of R times the probability of B. 3/11 times 8/11 is the 0.1983. Now let's calculate given probabilities. So we have a circumstance. What is the probability of drawing a blue ball on the second draw given a red ball was drawn first? We want to figure out if we draw red first, we could have 24 RBs, red blues, and we could have 9 red red. So if we draw red first, we have 33 possibilities. Now when we draw B on the second one, we have 24 possibilities of RB. So the probability on B on second given R on first will be 24 over 33, 0.7273. Now that's going to be slightly different if we change the order. What is the probability of drawing a red ball on the second draw given a blue ball was drawn first? In that case, if we go down the branch of blue first, we have 64 BBs and 24 BRs for a total of 88 possibilities. And R was selected the second, so that's 24 BRs. So our probability of R on second given B on first is 24 over 88, or 0.2727. Another type of tree is where you have the probabilities within the branches themselves. We have a litter of kittens available for adoption at the Humane Society. There are 4 tabby kittens and 5 black kittens, a total of 9 kittens. A family comes in and randomly selects 2 kittens for adoption. Now, of course, this is without replacement. They're not going to select a kitten and then put the kitten back into the litter to select again. They're going to select a kitten, don't put it back, they're going to take it home. Select another kitten, don't put it back, and they're going to take it home. So every time they select a kitten, the total number of kittens will decrease by 1. If we select a tabby first, there are 4 kittens to choose from out of the 9. If we choose a black kitten first, there are 5 black kittens out of the 9. On the second kitten that is chosen, it depends on what's chosen first, but the total of kittens left is 8. So if we chose a tabby first and choose a tabby a second time, there's 1 less tabby to choose from, so that probability would be 3/8. If we choose a tabby the first go around, 4/9, and then choose a black kitten the second time around, that's 5/8. 5 black kittens remain out of the 8. If we choose a black kitten first, there are still 4 tabbies left in the mix out of the 8. And if we choose a black kitten first, and then choose a black kitten second, there are 4 black kittens left out of the 8. So the probabilities are already within the tree itself. Calculating the probabilities is no different. So if we want the probability of tabby, it's going to be the 2 probabilities multiplied together. 4/9 times 3/8 is 0.1667. If we want a tabby then a black kitten, the probability of a tabby and a black kitten, in that order, that's 4/9 times 5/8. In other words, 0.2778. If we select a black kitten first, then a tabby, that's 5/9 times 4/8. In other words, 0.2778. And then 2 black kittens. 5/9 times 4/8 is 0.778. Calculating OR probability is no different, besides that the probabilities are within the graph itself. So what's the probability of choosing 2 kittens of the same color? That's going to be the probability of a TT or a BB. So we're going to add those probabilities together. Probability of a TT plus probability of a BB is 0.4444. Another way to represent data graphically is by a Venn diagram. It's a picture that represents the outcomes of experiments. Generally, it's a box of the sample space, and it has ovals or circles that represent the events. So we have 2 events here, A and B. You've worked with sets like this before, but now interpreting a Venn diagram. So looking at the sample space, it would be the values 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Set A would be the set of 1, 2, 3, 4, 5, 6. Set B would be 6, 7, 8, 9. Now let's go back to A and look for A prime. All the values in this sample space that are outside of A. So that would be 7, 8, 9, 10, 11, 12. What would be B prime? Again, those are all of the values outside of B but in the sample space. So you would have 1, 2, 3, 4, 5, 10, 11, 12. Now we want to find all the values that are in A or B. So those would be 1, 2, 3, 4, 5, 6, 7, 8, 9. We only count 6 once, even though they're both circling it. Speaking of which, the set of A and B is the value that they both encompass, which is 6. Calculating the probabilities using a Venn diagram is no different than what we've been doing. It's the number of elements in the set divided by the sample space. The sample space has 12 elements. The set A has 6, and therefore the probability of A is 6 divided by 12, or 0.5000. The set B has 4 elements. Sample set has 12, and therefore the probability of B is 4/12, or 0.3333. A prime also has 6 elements, and therefore the probability of A prime is 6/12, or 0.5000. B prime has 8 elements, and therefore the probability of B prime is 8/12 or 0.6667. When we look at the set of A or B, it has 9 elements, so the probability of A or B is 9/12 or 0.7500. And the probability of A and B, given A and B has just one element, the probability will be 1/12, 0.0833. You've reached the end of this lesson.